Happy Friday and welcome to GeoHug. So this week's rockstar is Stephen Micklethwaite. So I've been heckling him for a little while now to come on. So I'm very glad that he could join us today. So Steve is Associate Professor at the Sustainable Minerals Institute, and we'll be discussing undercover discovery and its implications in a socially and environmentally responsible world. So thank you so much for getting involved. It's wonderful having you.
Thanks, Jess. Well, this is, it's a real pleasure to be invited. Jess has been pestering me for a while, but the truth was I didn't have anything to say until now. And this is a bit of a different kind of talk for me relative to my career, because in the past I gave very technical talks as a structural geologist working with the minerals industry. But I'll get onto myself in a minute. The outline of what we're going to go through, as Jess said, is we're going to focus on discovery, particularly discovery undercover. But I'll be touching on things like mega trends that are driving that behavior in the industry, and on the implications of it. If you begin to think it through, the assumptions that underlie discovery, particularly in undercover environments, but also maybe in all sorts of extreme environments, such as where there's tough community challenges or water challenges. And then I'm going to speculate wildly as to what the future might look like, especially up to 2050. And that picture on the right is just to remind myself that I once was a structural geo. Right, briefly, the Sustainable Minerals Institute. For those of you who don't know much about SMI and where I'm based now, it's a massive research institute at the University of Queensland that spreads across 7 different centres, touching on minerals processing, health and safety. There's a centre of excellence based over in Chile. We've got work going on with land and environment, with water, and with community engagement, social responsibility. And the geologists of us sit here in the W.H. Bryan Centre. And we've been, as an institute, it's been a very successful institute, but probably more famous for some of the other centres' work in the past. And we've had some major programmes. I think well-known ones might be GEM, running in conjunction with Amira. CRC Ore began life within the SMI. There's a very long-running Amira program called P9. And this one here, COB, Complex Ore Bodies, is somewhat relevant to today's talk. And I'll get onto that in a second. And before I go any further, I should add that, I've had a lot of, there's probably a lot of collaborators in this talk, with particular shout outs to Rick Valenta, who's the director of both the Geology Centre and the JKMRC, and Karen Connors as well, who both helped contribute to this talk, and then latterly Mark Jessel, who's based over in the University of West Australia. So some of you, those of you who don't know who I am, this is my core business. I'm a geoscientist who has a lot of deep expertise in structural geology. And my career has spent a lot of time interpreting remote and geophysical data, doing field work, drill core logging, 3D visualization of the data, and also developing some technologies that hopefully assist with exploration. I'll just go back a slide to try and get that video working. There we go. But I stepped out of uni and became an exploration manager for a tier 1 company, and then have moved on from that back into very much industry focused research. And we're now I'm doing all this core business, but we're also looking at how we might extract great value from seismic, both 2D and 3D, and building drone related facilities. And here you're seeing a video of previous work where we developed techniques for generating really quick semi-automatic maps from drone data, extracting orientation information, and then turning it into a 3D model. And what would have taken months to years in the field is now taking days to weeks at most with that kind of technology. But to the talk at hand, what are the megatrends that we're facing as an industry going into the future that are both driving discovery and perhaps providing a barrier to discovery and the industry? So the first one, of course, is urbanization. And I'm sure there's been a few talks on GeoHug that have touched on the drivers. And if you look at the projections from United Nations as to what the population is going to be in 2050, it's touching on 10 billion people. And the majority of urbanization is going to be taking place in, I think, Africa and the Asian continent. There's also the push towards an energy transition, towards renewable energy, and also electrification of our current ways of doing things in industry. The barriers, though, are interesting because some of those barriers butt up and are really kind of coupled to the drivers. We've got community concerns and oppositional movements, which the industry faces regularly around the world. And that's connected and driving a sort of rethink in the industry as to how we identify ourselves and what our purpose is. And particularly companies like Anglo American, who have been discussing ideas such as what legacy can a company leave in a region that's a good and positive legacy post-mining. And then there's the demand for low footprint mining, for greater stewardship. And in particular, that's a very recent tragic incident with tailings has led to an overhaul of global standards. And I'll just briefly mention that in the talk. And of course, many resources are being discovered in extreme environments, and that's at depth, that's undercover, or that's in regions where there's a lot of jurisdictional risk or environmental risk, water and heat. And then the final point is both a barrier and potentially a bit of a driver. The push to autonomize and digitize what we do, how we mine, and the tools that the workforce have. And that means that we're going up a very rapid learning curve. It's an uncomfortable process, but it probably, well, very much an important one if we're also going to enjoy success. So just an example of some of the energy drivers for one or two particular commodities. Let's look at copper. Here's a recent publication from Watari, and he was looking at copper, and he looked at a whole range of metals actually, and I've just extracted out his predictions for copper and cobalt. And he's compared here with the orange dots the demand for copper and cobalt up to 2050, the projections for that with existing uses, and then the demand that's also going to come from low carbon technology in the blue dots. And you can see, but it doesn't really matter what the projections are, they're all increasing, and quite dramatically in some cases. And we've known this for a long time. So there's a real supply gap. There's the projected need on this graph on the right versus the current base supply. And we have some reasons to think we might be able to meet this, but whether or not we meet it, it means that there is a big drive in the market. There's a lot of pressure on copper. Copper in particular is a very attractive commodity to go for because it's a big market, and there's pressure on the price. So the prices are good, and the forecast for the prices are good as well. Yeah. And that's driving the industry's shift to go undercover. And this is quite a well-known, it's quite old now, actually, 2014. This is an analysis from Richard Shoddy, which he published presented in a talk to Society for Economic Geology. And this is for base metals globally. And he's just showing that over time, from 1920 to 2014, there's been a general trend towards discovery and extraction of resources at greater and greater depths. Although there is a bit of quite a significant difference between resources that are near field in the brown, near field to a mine, and resources that are in virgin territory in the green. But either way, there's still a trend towards greater depths. That's interesting because that has implications for both discovery and for mining. If we think about the amount of copper that's needed, and this is work that's really being pushed at SMI, and Rick Valenta has published on it. If we think about the demand for copper and we meet that, that means that by 2050, we will have to have produced 9 times the waste than we have done for the entire 20th century. So you're seeing here in that blue, dark blue color is the entire waste for the 20th century. And it's repeated in these stripes going forward. So you can see at 2050, the forecast projections for copper need means that we're going to be doubling our waste at an ever increasing rate. And the implications for discovery is that we need to be searching for large deposits, and in undercover environments with the economics of scale, you're looking probably at bulk mine deposits, and they're just adding to the problem because the bulk mining techniques and the scale of the deposits means that to an even worse degree, you're going to have larger and larger wastes produced. And this is really important because there has been a shift in the industry through the global industry standards on tailings, driven by the terrible Brumadinho disaster. This is driving a re-examination of our standards. And it's actually being partly driven by investors. Huge investors like the Church of England have come back to the industry and said, we will not invest in you unless you improve your game. So the kind of decisions we make at a discovery scale, which lead to the resources that are ultimately mined, has to be thought through carefully. And then I think there's a piece of work that needs to be done in terms of intentional discovery strategy in the light of a world that's undergoing investor-driven pressures. And in particular, it may even represent responsibility organization. You may get preferential treatment from investment in early stage discovery. One example, well, there's a lot of work has been done on non-technical risks, again in SMI, and again work by Rick Valenta, Eleanor Libra, and Deanna Kemp, and many others. And this map here sort of summarize it, published in a journal in 2019. What you're seeing here is a map of copper resources around the world at different grades, which are locked up. And they're locked up for various reasons, for complex ore body reasons. And when we did the analysis on this, it was very quickly realized the reasons for why these copper resources are not being mined today is not geology and it's not grade. It's 75% non-technical reasons. Permitting, social, biodiversity, jurisdictional reasons are keeping a lot of these resources locked up. And so that's led to the Complex Ore Bodies program at SMI. And if you want to learn more about it, there's a website down here. And thinking about these things for discovery strategy plays a role in the rest of this talk. So, is it getting all too hard? Time to take a deep breath. Maybe time to have a beer. Because I'm now going to talk a bit more geology and a bit more discovery. First of all, I want to just outline what I think are the general assumptions when it comes to undercover discovery, particularly searching for discoveries at greater and greater depths. And this is something Australia is taking very seriously. We've had the Uncover initiative. It's been a very successful initiative, in my opinion, because it's led to the release, the support and leverage of hundreds of millions of government fund, hundreds of millions of dollars of government funding for geoscience organizations. It's led to the establishment or assisted in the establishment of the Minerals Exploration CRC. And it's driving a lot of thought and thought leadership in this country. So anyway, the sorts of assumptions are that if you look at a map of Australia, where existing resources are, most of them correlate with outcrop or near geology. So there's a large proportion of Australia that is covered and remains unexplored, and there's no reason to think that this density of deposits that we find in these places can't continue in these covered areas. So obviously there's a large virgin territory with great opportunities out there in that assumption. But there's some caveats, because as you get deeper and deeper, costs get increasingly higher and exploration techniques get increasingly lower resolution and higher risk. You know, things like geophysical vectoring, remote sensing can't work because it's a near surface technique. Geochemical techniques can work, but they are limited by the depth of the cover. It becomes a higher and higher, more and more risky enterprise. So that implies that if you're going to explore for anything in these undercover regions, then you need to be exploring for big prizes, for world-class deposits. There's no point for the economies of scale and for the risks involved to just be looking for your sort of normal size deposits. And one implication of that is that you should be taking district scale positions to explore and uncover. Value also is probably only going to be suitable for some metals, particularly the base metals, and probably only certain deposit types, porphyries, copper porphyries, because we have a very good deposit scale model for porphyries. They might be very amenable for discovery undercover, sedimentary hosted copper, and maybe Broken Hill type base metal deposits, things like that. But it's not going to be an enterprise that is permissive for every deposit type. Particularly narrow veined commodities that are hosted in narrow veins, typically, they're going to be very hard to explore for in these areas. And because of the costs involved, another assumption is that we need to accelerate the timeline from area selection through to resource definition and modeling. And one of the underlying economies, factors that are driving the economic considerations is that the deeper you go, we're going to be limited to certain mining methods because many other mining methods just won't be economic. So you're really looking at block caving or sub-level caving methods, as shown here in this diagram. Now, these assumptions, some of them are right, but the rest of this talk, I just want to have a look at them because I think we can actually poke holes in some of these assumptions, and it's certainly worth questioning them. So let's just go to Queensland and have a look at the trends we're seeing in this state where I'm based. So this map on the right is Queensland border, and you're seeing the depth to basement model underlying, and then contours of the depth of that basement shown with these blue lines, and outcropping regions of near surface geology where there's a lot of deposits, existing deposits shown in the white. The first thing to note is this is the 1,500 meter depth contours, and that's the 1,000 meter depth contour. So basically between the outcropping regions and the 1,500 meters depth, those are the sorts of limits at current mining methods that will be economically viable. So you can see from this map that there's a very rapid deepening down to Proterozoic basement that takes place. So really, the search space for undercover discoveries at the moment with current mining methods is not the whole of Queensland. It's limited to the area shown there. If I overlay on here where the outcrop is and where the existing exploration mining permits are in covered regions, which are shown in the yellow polygons, you can see a pattern where that most of the existing permits are clustered around the margins of the outcropping regions. And that's a good thing. I mean, it just makes sense because in these areas, you can extrapolate out the known geology undercover and you can lower your risk. And that's an important strategy going forward. But it does mean that there will be opportunities in the future where we think once our methods begin to improve in exploring undercover, that some of these other areas out here where the geology is much less well known at surface, they still represent opportunity for discovery. But there's a caveat, and this caveat relates to the mining methods. If you overlay on that map where the Great Artesian Basin lies, then almost all of Queensland is covered by it. And that's a very, very important water resource for the agricultural industry and for Australia as a whole. And it therefore has certain restrictions that surround it as to how you disturb that water resource. And we don't really yet have a clear idea of what mining methods are going to be allowed through that cover sequence that contains the Artesian Basin. But I hazard a guess that caving methods might not be permitted. And so this needs to drive our discovery thinking in terms of where we can extract resources economically with more favorable methods, or it should drive our mining, our research in the processing routes as to whether we can develop new methods that will unlock the resources at deep depths without negatively impacting on the cover. Right, so a quick drink. I'm going to change tack now and quickly do a thought experiment and use a little bit of probability thinking. And there's going to be a lot of people in the audience who understand probability a lot better than I do. So what I'm doing here isn't an analysis that I think is correct. It's just an illustration of the kind of thinking that I think we're going to require moving into the future. But to do that, I'm going to be talking about vectoring and targeting towards deposits and making successful discoveries. And that is, the concept of vectoring and targeting is actually scale dependent or mode dependent. So there are vectors and targeting methods that we all know and love, like there's mineral chemistry, you can use magnetic, and you can search for magnetic anomalies, you can search for gravity anomalies, and so on. And those are techniques. But then there's vectoring and targeting systems. That's when you take that raw data, your mag and your grav, and you begin to do a lot more analysis on it, and you begin to extract value from it. Inverse and forward modeling, particularly if it's constrained modeling, interpreting that data in terms of geology, thinking about it, simulating the systems and how you might forecast potential targets within a region from the data that's sort of hidden in the magnetics and gravity. And then finally, the final scale is thinking about a vectoring and targeting ecosystem, which is really a collection of these systems. It's where you combine your mag-grav system with other techniques to really lower risk. And that's the point about discovery in any game, but particularly as we go deeper undercover, the way we're going to do it successfully is to lower risk, and to lower risk in a way that we haven't achieved yet, I'd say. So if we're going to find and look for world-class deposits, real giants, those are rare occurrences, even in outcropping regions. And there's analogies here with the detection of rare disease, diagnostics of rare disease. And if you coming at things from a Bayesian perspective, which I barely understand, but if you're really trying to understand probability of you having a rare disease when you've just received a diagnosis that you've got it, or you've just had a test, I should say, that suggests you've got it, then there's some interesting dynamics. Now, let's imagine that your test is 90% effective. So you go to the GP, and the GP says, I'm sorry, I've got some bad news for you. You've tested positive to this rare disease. The first thing you should do is not accept that. Because a 90% effective test in a rare disease where you might have a population of 100 people and only 1 in 10 ever catch that disease, but the test itself is 90% effective, that implies that there's at least 9 false positives in the population. So in fact, the real risk of you having that disease for one test is much lower than 90%. So what you do is you go and get a second test and you update the evidence. You update your understanding of how likely it is you've got that disease by getting a new evidence. And that's exactly the same process, same logic we follow with discovery. So we can develop great vectors and targeting workflows that have high levels of confidence, that we can have high levels of confidence in. But because world-class deposits are rare and deposits themselves are rare, the probability of finding a deposit is still very low, and it's a high-risk game that we play. So how do we row a risk in situations of low likelihood? And I think one of the powers of thinking about this problem from a Bayesian perspective is it tells us that if you collect evidence, it restricts the space of possibilities. It gives you more and more chance of making a discovery. And every time you apply a new vector or technique system, you can lower the risk, that you can increase the probability of discovery if it's a positive outcome, or you can screen the system and decide to walk away. So I've just done some really simple-minded, naive calculations to illustrate that point. Right. What you're seeing here is the probability of discovery of a world-class, of a deposit. Sorry, not necessarily world-class deposit. And I've applied vectors that have different effectiveness levels, if you like, or probabilities of success. And if you have a succession of vector systems that have a likelihood of success that is less than half, you are actually destroying discovery value. So this implies that bad techniques applied to discovery don't just fail, they actually mislead. And I think we can all recognize that in the game of discovery, because we know we've all experienced applying technique where you might see a large number of anomalies, and if you were to properly test all those anomalies, you would be spending more and more money and more time, and you won't really have a guarantee of success. The other thing that's interesting is this sort of analysis suggests it's really, really important to benchmark our vectors and targeting systems. I'm not talking about the individual techniques, I'm talking about the whole system. How effective is that at finding a deposit? We don't know at the moment. We haven't got a clue with whether most of our techniques are less than 50% likely to lead to a discovery if we get a positive result, or more than 50%. So there's some really critical research that's got to be done there. In this analysis, this is the same graph, only I'm just looking in this at the vectors that have a greater than 50% likelihood of leading to a discovery. And we're also looking at world-class discovery vectors, we're looking at the probability of searching for or having success at finding a world-class deposit. And when you look at a graph like this with probability on the right and the number of vectors you've applied along the x-axis, there's one interesting observation. Just the form of the maths means that if you have very effective vectors that if they return a positive diagnosis, if you like, or detection, if their probability of success is greater than 0.7, then they're all clustering towards the left-hand end of this graph. In other words, you don't need to apply many of them to really begin to lower risk in a discovery scenario. But there is a bigger and bigger gap to the less effective vectors. So this suggests that we need to begin to maximize the value we get from our vectors to begin to really lower the risk when we apply them in a discovery sense. And then this final step doesn't really add a huge amount of value to the argument, but what I did here was, I stepped back and said, well, okay, if we apply 2, 3, 4, 10, 14 different types of vectoring or targeting system to a region, it's very unlikely that they're all going to have the same probability of effectiveness. That if they return a positive result, they're not going to have the same probability of leading us to that discovery. So that, in other words, they're going to be varying in their effectiveness. So what I just did was I ran a Monte Carlo simulation where the effectiveness of the vectors varied over a few thousand simulations, and then I plotted that up. And the take-home message: this is the probability of effectiveness for a sort of a standard discovery, and this is the probability of effectiveness for a world-class discovery. And I guess you can see that in this slightly more realistic world, risks do lower rapidly. If you have 3 or 4 or 5 different vector systems that you're applying to a permitted area, and they're all beginning to return positive indications that there's a deposit nearby and that you're in a fertile system and you're getting closer and closer to that discovery, the risks lower rapidly in both systems. And interestingly, there isn't a great deal of difference between finding a normal deposit and finding a world-class deposit. In other words, if you're in the right area, the chances of finding a world-class deposit aren't massively different, and so that's kind of encouraging, a bit of good news for discovery undercover. So the implications of that thought experiment is, there's no way that we can expect to successfully screen an exploration lease area with just a small number of techniques. And one potential way of doing exploration is to run maybe some soil sediment analysis sample campaign, and to do a little bit of magnetic or gravity geophysics, and then to begin to move directly to drill testing. And you can do that, but when you move to an undercover environment, and particularly as you get deeper and deeper, drilling is one of the most expensive techniques that you will be applying. And it's an important tool for vectoring and targeting in its own right, but you probably want to stage drilling to, or significant drill campaigns toward the middle and end of an exploration campaign within a permitted area. In other words, you want to really start out and take a lot of time maximizing value from your geophysical and, if appropriate, geochemical survey techniques and the systems that you develop of interpretation around those, and only use the drilling to begin in a small way to update your geological models and lower your uncertainties on that model. So that has implications, of course, for this idea of accelerating timelines. I'd suggest acceleration of timelines in exploration undercover are probably best done in a staged process where you start out slowly, you take a lot of time to apply the most appropriate techniques and maximize value from them. And then you begin to ramp up your efforts in years 3, 4, 5, and so on. And then the other implication is exploration remains a low numbers game. We do not have a good measure of how effective our vectoring and technique systems are. And this can be quantified. And I think there's real value in exploring how effective they are in undercover environments and even in exposed environments. So we need to benchmark the effectiveness of our techniques and targeting approaches. We need to have approaches that quantify uncertainty and then design our exploration programs around lowering that uncertainty. And we need to obviously be applying multiple vectors in the at least somewhere between 4 to 6 or 7 different systems where you maximize the value from each of them in order to really have confidence that you screen an area properly and you can walk away or move to a discovery. So what do other sectors do to achieve this? And of course, the big brother is always oil and gas sector. And I think in an undercover discovery environment, what we are seeing is a demand and a need for the geophysicist, which isn't yet being routinely realized in terms of the kind of people that companies are employing. Geophysics has really been on its nose in terms of undergraduate numbers and employment opportunities. But the near future suggests that that's going to turn around. We not only need geophysicists, but we're also going to need geologists who are competent at converting geophysics into geology. And oil and gas industry do this routinely. And one of the things that they do is they actually increase, in some ways, they've increased their need for field work. They employ analog field studies. So they can't explore for oil and gas in deep marine environments, but they can go to analog field sites and really pull those apart carefully and understand them in detail in order to inform their exploration models. Then the kinds of geophysics that they apply, obviously the most obvious one is seismic. They get the most out of that. They don't only get the most out of it in terms of interpreting the data afterwards, but they get the most out of it in terms of collecting it. They go to town with forward modeling, how your survey should be designed, what kind of signals you should be expecting, and then the processing of the data. And I think in an undercover discovery sense, that's exactly what we're going to be having to do. We're going to have to improve, to some extent, the way we design, acquire, and process our data in the first place. And then finally, this point again of maximizing value from it. And here's just an example of how the petroleum industry do it. What they've done here is they've collected seismic from an environment, and they have begun to interpret that seismic in terms of a stratigraphic fasces model, and they've got a huge amount of detail in there. And they link their interpretation process with forward modeling of what stratigraphy should be doing when it's being deposited, with the impacts of diagenesis in this case. They're applying rock physics, then they're doing seismic forward modeling to try and improve the quality of the data, and it iterates through. And this is a sort of workflow that they're going through to really maximize value from the data before they ever sink a drill hole. And the implications for undercover discovery in the minerals industry, as I've mentioned, there's economic pressures, particularly a demand for our return on investment, which is always going to be a very tricky balance when you're looking at a high risk game, trying to successfully explore for discoveries undercover. So I think the economic pressure means that we're going to have to follow a very similar trajectory to the oil and gas industry. And in some ways that's good news, because despite the rise of technology, including AI, I know a lot of fellow geos who are feeling that their jobs are somewhat threatened by the rise of geology. But in the petroleum sector, I don't think we've necessarily seen a loss in geo skills or in geologists. If anything, the petroleum industry is very good at employing high quality geologists, building geological teams, and increasing their knowledge, which they then partner up with the technology. So as we move to a world of improved digitization in the workforce, there's going to be a need to hardwire our skills into the geological modeling and simulation workflows, and there's going to be a need for fundamental geoskills. We just can't afford to lose that if we're going to actually do this successfully. And again, you know, this isn't a talk of gloom. There are some really promising developments on the horizon and some very promising techniques that we already have in our hands. And I'm just going to show you one here. This is the Loop consortium that's being led by CET, University of West Australia, and Monash University, through people like Mark Jessel, Laurent Elier, and others. And what they're beginning to do is they're beginning, if you look at this diagram on this very complicated flow chart on the left, they're taking gravity and magnetic data and they're linking it together with geology information, petrophysics, you know, the physical properties of rock, existing models, and then they're using it, combining all that information to simulate in 3D what the geology is and quantify the uncertainties and really extract multiple realizations of what the geology looks like in 3D. And it's a complicated but very promising approach. And what I really like about it is Laurent and Mark and all their co-workers, although this diagram is complicated, they are communicating this in a way that every geologist can pick up. And it's been publicly funded and is very much a high-profile development that's leading to open source codes and solutions that we're all going to benefit from. And here's just one component of that. This is the map to Loop module within Loop. And what Mark and co-workers like Mark Lindsay and others have achieved is they have been able to take digital maps, simple geology maps, and they've been able to extract a whole range of information that's contained in those maps that we don't normally think about in order to automatically generate a 3D model. And this process of taking a digital map with a few measurements, with faults in, with complicated folded geometry, leading to that 3D model that is permissive with the geometries here, that takes 15 minutes with a bit of code. So I think there's, at our fingertips, there really is an opportunity now to speed up and accelerate our workflows through these technologies that are emerging, and to maximize value from the data that we routinely collect. So just moving towards the end of the talk, just a few other thoughts. Now, one of the other assumptions was the mining methods that I talked about that underpin undercover discovery and discovery strategy. And that is changing really quickly. So some intriguing mining methods that are emerging are things like in situ recovery. And in situ recovery in the past has a terrible name because it's led to some environmental disasters. But there are different lixiviants, leachates that you can use that are much more environmentally friendly. And I'll go into this in a bit more detail on the next slide. There's also autonomous precision mining. So as you begin to mine at depth, if you're actually going to go for a mine that's a little bit more conventional, it's going to be all about minimizing dilution, potentially removing the human from the environment, and accessing areas with smaller amounts of waste generation and so on. This actually, if we get this right, it means that we won't necessarily need to employ bulk mining methods to extract resources undercover. So we could actually go for high grade, large, narrow resources as well. I've mentioned finer mining waste, but we'll just move on from that. And the question exists is how deep can we mine? You know, the deepest mines presently are in the Vits. They're about 4 kilometers deep. In Australia, we can never reach those depths with current mining methods because the stress state's too large in the crust. But with something like in situ leaching, where you're using drill strings to get underground and you never actually have a mine, it's mining without the mine. Well, we know our drilling technology can go down to 12K. I'm not saying that's economically viable in the minerals industry yet, but at least technically we can reach those sorts of depths. So it does open up the range of possibilities of where we mine. And this is just a paper that's been published literally, I think, this month in Science Advances, employing a new approach to in situ recovery, where they actually not only put the drill strings down with a lixiviant, but they discharge an electric current, which actually mobilizes the cations and anions through the groundwater and leads to much more effective ways of recovering the metals. When I see things like this, I think we have an opportunity to flip our thinking. Routinely, what we do as a discovery geologist is we go out and find resources, and then we hand them over to for a feasibility study, and then to the mine planners and the process engineers, who then work through the calculations of whether this resource is going to fly or not. And that leads to a lot of technical failures, where we found something, but economically that it just isn't quite going to make it across the game line. I think we should start flipping our thinking. And the reason for that is it takes around 10 years maybe to find a deposit on a piece of ground, particularly in an undercover environment. It can take up to another 10 to 20 years to turn that into production. So if you have a decadal period to play with, we should actually be talking with our geometallurgists and our process engineers about the technology that's emerging that isn't currently available. And we have the potential to explore for resources that on present day economics are not economic, but we have high confidence they will be economic within 10 years' time. And so again, that opens up the search space. And then finally, this talk was advertised as what does the movies Tron and The Matrix have to do with discovery? And I think that really plays into this question of how we go about digitizing the workforce. And I hope, you know, I haven't really said it specifically, but the techniques that we employ going into the future have the ability, have the opportunity and potential to empower us and not disempower us, to accelerate what we do rather than replace us, and certainly not to turn us into automatons. So in Tron, there was a kind of fictional world envisaged where human beings very much became part of the technology and drove it and were the commanders in the technology. Whereas in the Matrix, you were living in a world where you were very much disempowered. So I think we need to be Tron in the future rather than the Matrix. And you know, as we move to this future, there's potential it can accelerate human expertise. It can involve us in new ways where there's not only is the technology accelerating our workflow, but we're still very much in the loop, checking the uncertainties, but doing so much more quickly than you would do with standard field techniques and logging techniques and so on. There will, of course, be a need for an upskilled workforce, and this leads to question marks over how are we training our geos in university and how is industry helping support that initiative. But there's also potential for fun. Yeah, we could potentially open up need for more field work, not less, and the gamification of how we work. And I think the other final thing I'd say about this is it could go badly. But if the narrative where it goes well is the narrative where there's optimal outcomes from this digitization, not an optimized workforce. In other words, at the board level, decisions are made to not cut or get rid of exploration geos because technology is allowing us to do so, but to keep that expertise, because by doing so, combining that expertise with the technology, you empower the geos to do far more than they've done before, to accelerate, to explore much larger areas and to do exploration in a much quicker and efficient way. So finally, the last thought I just want to leave you with is I believe we have all the technology and skills available now. I've talked about how technology is going to change in the future, but to actually make an undercover discovery now, we don't actually need any of that. We have all the tools at our fingertips. And Australia has a great track record. I've just listed some names here, but Olympic Dam, Cannington, Ernest Henry, Nifty, the most recent Julimar discovery, these are all undercover discoveries. And so there's something encouraging about that, and also something intriguing in thinking about how society at large has had a bunch of technologies that have enabled us to do quite amazing things, which we haven't necessarily kept going with. It's been 2 decades since supersonic flight was a commercial reality. I just saw a documentary on this. Supersonic flight was actually economically very profitable. They didn't stop it because it wasn't profitable. There were other factors involved. The space shuttle has been 2 decades since that was retired. The last moon landing was 49 years ago, over half a century. That's incredible to me. An Olympic Dam was discovered undercover 46 years ago. And good science was an important part of that story. So that just encourages me that we can do this, and we have all the skills we need to do it right now. So thanks for listening.